With one more presentation, medically speaking, and I got to tell you guys, every commissioner here will say, "Hey, listen, I got the best doctor in the country working ringside, cage side, and wherever else side you have. I take care of basketball and everything else at Mohegan." But I got to tell you guys, I got the best doctor around when it comes to the chief ringside physician at Mohegan. So, and I don't say that very often, and he's in the room, which I usually never say it in front of him. But I did do it today. I don't know why I did it. But with that said, hey, Dr. Michael Schwartz is also the co-chairman of the medical committee because he lives, eats, and sleeps this stuff. So, as Doc, are you in here? Yep. Okay. Where? Oh, shit, I didn't know he was in here. Here's Dr. Michael Schwartz. Thank you. Here, Doc. Hey, he's so good. He's actually my general practitioner, too, so he does bill me.
Let's not talk about the exam again. Okay, thank you. When Dr. Mosey came up and spoke about CTE and TBI, obviously that is one of the biggest topics around today in all sports, all ways of life. We talk about high school and pee-wee football players not letting our sons, daughters play anymore because of concussion risk, and that translates all the way up into what the NFL is doing. But until now, there was no real treatment. And a lot of companies have worked on things, a lot of pharmaceutical companies have come out with things, and so far, they're not really working. They're not preventing the long-term sequela of chronic brain trauma. And as Dr. Mosey said, the symptoms are horrible. It's a progressive loss of who we are. It starts with disorientation, memory issues, cognitive dysfunction, and then it leads down the road to, an Alzheimer's dementia type process, and then death. So a few months ago, I was approached by a pharmaceutical company who has found a very unique molecule that may be able to slow or stop the progression of CTE. This would be game-changing, obviously, and it's very early in their research, but it's something that's never been done before. And a matter of fact, I'm going to bring up the lead scientist and CEO in a moment, but I believe it was almost found by mistake. They were looking for something else, and they found this molecule that had very, very unique functions. So what I'm going to do for you first is I'm going to play a short video, and then I'm going to bring up Sara Isbell, who's the CEO of Mercaptor Discoveries.
The Captain story is about an extraordinary discovery with the potential to be a game changer in the realm of brain injury. It begins with a surprising result in a research lab that, upon further investigation, revealed a molecule with the potential to treat both traumatic brain injury, also known as TBI, and its long-term effects, including CTE. We named the molecule Captain. So, what's so special about Captains? Captains may be the key to a breakthrough treatment for people who suffer the effects of concussions and repetitive head trauma. Athletes in contact sport, as well as military personnel, are at high risk for trauma to the head. TBI has been associated with progressive brain diseases, including CTE, Parkinson's, and ALS. Mercaptor's Captain technology opens the way for potentially breakthrough medical treatments, especially for conditions caused by brain trauma. The brain floats in a protective fluid within the skull. When the head is subjected to violent motion, a phenomenon known as axonal shearing occurs. Axonal shearing happens when one layer within the brain moves a little faster than the other, causing straining and tearing of neural fibers, triggering the gradual spread of damage to areas untouched by the initial injury. When nerve fibers are damaged, the complex processes behind thought, feeling, action, sensation, and memory are placed at risk. Uncontrolled storms of abnormal activity rattle the brain. The damage ripples outward, destroying additional tissue, leading from injury to progressive neurodegeneration. Captans are designed to rescue brain cells by attacking toxic byproducts generated by brain injury. Captans calm the storm, restoring control over excessive signaling and its consequences. Captans are engineered to act only at the site of injury and only to the extent necessary. The ability to target damage at a local level is historically unprecedented and would revolutionize brain medicine. In these two cross-sections of the brain, we see brain trauma with and without Captan therapy. Initial damage is irreversible, but drugs developed from Captan research will be directed at preventing the damage from spreading, reducing the chances of serious long-term consequences later in life. Our team is excited about what Captans could mean for the future of athletes, veterans, and anyone who's experienced a traumatic brain injury. Once fully developed, this technology could help millions. We have the momentum, and we'd like you to join the fight. Team up with Mercaptor Discoveries to beat brain injury.
Okay, I'd like to bring up Sara Isbell, CEO and lead scientist at Mercaptor.
Hello, everybody. While we get this presentation loaded, I just want to thank you, Michael Schwartz, for allowing me this opportunity to speak with you guys today. He mentioned that we kind of found this by mistake, and that is true. Discoveries. Hold on. Okay. Do you see the drive? No, we're in the drive. Scroll way up. I'll say PowerPoint. Oh, you're in a folder. Go back to F. Yeah, there, that one. So we were looking at these small molecules, and we were looking at them for cystinosis, fibrosis, and these other diseases. We looked at them for about 6 years, and we thought we knew everything there was about them. We knew their metabolism, we knew how they went into the brain, they increased antioxidant behaviors, and one of the last things we decided to do with them before we started moving forward into IND in the clinic was we ran this Huntington's disease assay with Huntington's disease cells. And we looked at 50 of them, and we expected them to all behave the same. But they didn't. There was this one molecule, this one that just stood out from all the rest. And as scientists, we started to ask ourselves, well, why? You know, let's not put this one aside. Let's not think it's an anomaly. Let's look at what it could be doing. So as we started to study it, and our CSO and co-founder is a brilliant chemist, and a lot of what we do is biochemistry, we started to look at the possibilities of what this molecule could be turning into where there's damage. And when we did that chemistry, we found this molecule that was oxidized. If it was reacting with the damage, it could be, you know, picking up the ROS, binding to the free metals. And when we looked at that molecule and did a search for it, it was found to be a neuroprotectant. Not only were our molecules increasing glutathione, or these properties that allow for radicals to be dumbed down or to be quenched. This molecule, after doing that, was a neuroprotectant that was already known but could not be used because when you give a neuroprotectant that stops the brain from firing, as you saw in the video, it goes throughout the whole brain. You know, you can't silence the whole brain, so it becomes very toxic and they're unable to make it to the market. So what we did was we took the properties of this Kapton. We kind of figured out probably what it was doing. We created a new company based around this called Mercaptor Discoveries. We actually created the company we're working at called Raptor Pharmaceuticals, and it got purchased about 3 months after we found this discovery. So we had to move quick. And we got the IP, we licensed it from the company who purchased us, and we created this company around focusing on what we now call Kaptons. A thiol is a mercaptan, and these molecules are based on thiols. So that's where the word Mercaptor and Kapton comes from. And so we've been working for about 2 years to test our hypothesis if you do get conversion only where there's damage, and so far that is what we see. Now, let me just go through this presentation here, and one thing I want to talk to you about is neuronal signaling. There's 2 neurotransmitters that balance whether the brain neurons are firing or not firing. Glutamate is the one that's used to fire the neurons. It's very important, but it's also extremely toxic. So the brain balances that by another neurotransmitter called GABA. And GABA's not on here. But GABA is the opposite of glutamate, and it'll actually silence the brain. So you have this balance that's going on all the time in the brain. Now, one thing to point out is that inside a neuron, there is 10,000 times more molecules of glutamate than outside. So you can imagine if a neuron was to pop or was to rupture, you're going to get all that excess glutamate into the surrounding tissues, and that's going to cause this storm. And this storm is what's going to propagate outwards, and that's the progression of the disease. Now, this is what I call the toxic cascade of the glutamate storm. And I think there's something here to play, though it took a lot of memory, so I don't think it's there. So if you get any deviation within the glutamate and the GABA and a lot of glutamate, you're going to just get a lot of firing. And in the case of brain injury, that's when you get this increase of extracellular glutamate. And they don't directly kill the neurons, this glutamate, but causes the neuron to go fast and fast and fire and fire. And mitochondria inside cells are the energy for all our bodies. It's the currency for energy. And so in order to fire, you need to really kick up energy. And the mitochondria start going and going really fast. And all of a sudden, they can't handle it anymore. The mitochondria will then pop, die, and that triggers the apoptosis, or the death of the neuron. And then you get this storm, and I like to think of it as like you have a pond, and you drop a pebble in that pond. You know how you get the ripples that go out? Now, some things, such as acute diseases like TBI or even CTE or stroke, that's fast. That's propagating fast. But in long chronic diseases like Parkinson's and ALS, it's a slower progression. So progression can be different. Now, some truths about TBI. First, a little bit about the brain anatomy. This I won't go through this slide too much. It kind of just shows that different parts of the brain control different things, like your speech, your emotions, and how you think, and that sort of stuff. Another thing that you saw in the video is the brain is gelatinous. It's actually really like Jell-O, and it can squish and constrict. And it floats inside of the skull. It's not attached to anything. It's just attached to the spinal cord. So you can see if you are accelerating really fast and you were to stop, the skull stops. And then the brain is still going to go forward and hit into the skull. That's acceleration. Deceleration causes rotational and angular motion. So pretty much the brain is twisting inside. And this part of your brain down here gets a lot of the torque. That's involved in emotions. And that's where you get a lot of, as you see, is these people that have TBI, that leads to CTE, they start to have a lot of emotional control, right? So TBI injury cascade, there's a primary injury, and that's when the axon will shear. It's when the brain hits in, the two layers will move, and you get shearing. This cannot be treated. This is something that maybe with equipment, with training and new safety rules, this part can probably be mitigated. Now the secondary injury, and this is very interesting, the secondary injury, your behavior will actually come back faster than the tissue can repair itself. So when you have a concussion and someone is suffering concussion symptoms, they'll seem all better, maybe in a few hours or days or a week, and you say, okay, person's better again, let's put them back out. But the secondary injury with the tissue damage, that is still there. And they call this the invisible injury. And mild TBI, if you have this over and over again, these little, traumas to the head, that tissue is actually building up each time you have a little hit. That's why they say that second hit can be worse, because you're adding an effect on top of what was still already there damaged. You get swelling and rupture in the secondary injury. This is so after the neurons is torn, everything starts to swell. You get inflammation. This is when the immune system comes in, and you start to get with the swelling on the brain. You know how that can then be bad and constrict a lot of the blood flow. You also get loss of the neurotransmission. So where the brain cell has ripped, you can't signal there anymore. And that in itself is also going to start killing the neurons. They pop, they release more glutamate. We won't go into that. So again, it's weeks to months that this tissue damage could last, even though the behavior may come back in a few hours or days. And it does, when a neuron can't communicate to the next neuron, the other neuron just dies. If you're not getting input, again, the neurons die, so it's just part of the cascade. The tertiary part, this is the pathology. This is the disease symptoms, where you actually start seeing, say, Parkinson's type, or ALS, CTE, and it's that tertiary part that we are trying to prevent. We're trying to mitigate after all these mild TBIs of getting to that pathology state. Now, just really quickly, we won't have to look. This is just showing that when you get hit in the head, you can see the brain, how it slams up against a wall or whatever stopping it. The brain will go up against the skull. You get your rotational. On the bottom left there, you can just see that's little cross sections of the outer white matter, or the outer gray matter and the white matter that shift among each other when you hit tearing. Let's see if this one will work. Okay, the videos are loading. But again, this is just a little video with a cross section that shows you how the brain hits the skull and the axons will rip. Oh. Okay, so the brain hits the skull. This is a cross section of the gray and white matter. And you can see just the vibrations, just that jiggling can actually cause them to rip. I thought I zoomed in there. This slide, again, is a little bit busy, but I just want to show you that you can see where, again, how the axon, it rips in the middle, this bulb starts to form, it releases the glutamate, and you can see the areas here in the brain where you can have, if you get one hit, you could have this happen in multiple little parts of the brain. And the key point here is you're releasing 10,000 times for each neuron into the cell of glutamate. the excitatory neurotransmitter. Here's just some images of the secondary injury. You can see you get a lot of scarring around the area where it happens. This scarring can build up plaques because when the neuron rips, you also release a lot of tau and amyloid, and you build up all these plaques that you might have heard of, you know, in ALS and Alzheimer's disease. And here again, I'm just showing that different areas of the brain that get injured lead to different types of conditions. So you could see, it's small for me, on the top left one, that can lead to Alzheimer's. The darker color is where that initial injury happened, and you can see as it spreads, you can see if you get hit or damage in the bottom left, that would be for you. You can lead to Parkinson's disease. So all these neurodegenerative diseases, regardless of how you got it, genetic or a hit in the head, all have this underlining mechanism of excitotoxicity. Okay, so that's one point I really want to drill home. So where do captons fit? Like, what are they doing? What was that one little piece that we found at the last minute? Well, do they stop primary injury? No. Again, that has to come to safety and equipment, education. But that secondary injury, where you get the swelling and you get the rupture, that's where captons come in. When you get this rupture, you release a lot of toxins, like the dark cloud that you saw in the video. What we have found is that you can have a molecule that where that black cloud is, it will react with it. It'll actually bind to it. And by binding to all that, it turned into a known neurotransmitter. This is why we say we're injury activating and localized. So captons, yes, this is where they can come into play. They will slow down the progression of the storm by mopping up all that dark and allowing the brain to heal itself. The brain's really good at healing itself. It's just when there's too much damage, it just can't handle it. So captons will come in, relieve that damage, and the progression leads to the tertiary injuries, such as your emotional instability, which is down here at the brainstem, and ALS, and these others. So, and CTE. All right. This is where, okay, so now I'm just going to talk a little bit about why we're so convinced we have something here. For about 20 years, researchers and scientists know how to stop excitotoxicity. There are drugs that they know will block. You could block glutamate. You can increase the GABA, which members silence it. You can block calcium influx. And I say that because in order for a neuron to also fire, it needs a lot of calcium. So there's a lot out there that could stop excitotoxicity, which means you could stop the progression of all neurodegeneration. And when you have a TBI, a mild TBI, it will isolate right then and there because it turns on only where there is damage. Now, as I said before, there's a problem. These have been in the clinic. Billions of dollars have been put into these molecules, and they just can't dose high enough. If you give a patient a whole lot of this molecule, your brain is going to cease. Your blood pressure goes up. You can tell there's a lot of reasons why you can't do that. So now we've been able to find, based on the chemistry that we know of that one we found, there is about 6 drugs that are out there that fit, that we can what we call captonize. And what that means is we take off part of that known neurotransmitter, and now it's allowed one thing to go into the brain. It's non-toxic. You could take one a day. You can just have it on board. You don't need to have your injury before you take the Capton. So the Capton's there, it's on board, and when you get hit, when you suffer an injury, it's going to turn on. Turning on, it's going to react with those toxins that are released. It's going to become something that blocks glutamate. We can make them so it increases GABA, and we can also make some that inhibit inflammation. And can you imagine being able to do this right at that site? So now you can dose higher. You can give a much higher level of the drug. You can get it into the brain at a higher level where it is neutral and not toxic. And then when you have an injury, it'll come on locally at that high concentration, but it's just there. And so the rest of your brain is unharmed, untouched. And this is my team. We're a very small team. We've actually been together since we started Raptor, most of us. And our plan is to stay small. And we outsource a lot of, our animal studies and work. And by staying small, we're very efficient. We follow the data. We don't need to have a management meeting to a management meeting to change what we're doing. And we just follow our data, and our overhead costs are very low. So with that, I'd like to say thank you. I hope that wasn't too much scientific. I'll take questions.
So I think this is very exciting because, to simplify it, this may be something that a fighter, a football player, somebody in the military could take once a day, almost like a vitamin. And it would be there in their brain so that should they encounter an injury, there is already something that's going to protect the brain and not allow this whole cascade to get out of control. It could also be given after the fact, obviously, but I felt when I heard this that this could be a real game changer in what we do, and not have to see our fighters 20 or 30 years down the road who don't know their name anymore. So anyway, that's why I brought Sarah here, and I think this is interesting stuff, and we're going to keep you all updated on her research and her progress. And if there's any questions, I'm sure.
Can you talk after the fact, like when you're primary, secondary, tertiary?
Thank you. How long after secondary, would you say, or how long after primary for the healing still, if you're say they're secondary?
Yeah, so obviously it depends on the amount of impact, if you're talking about TBI. If you have such a hard impact, you go into a concussion, then that can last a lot longer to primary. And they say to get to secondary, it could be about 2 days to 2 months. And then to get to tertiary, that could take years. So it kind of depends on that initial impact of how much damage.
And say things like Parkinson and ALS, do you think if at that point there could be reduced, maybe?
Yes. So
severity?
I know you heard a talk earlier about CTE. So when you have TBI and TBI progresses to CTE, and that then can progress to either Parkinson's or ALS. When you start taking the Kapton, say you take it when you start showing signs of Parkinson's, the idea is instead of it being a few years till you're immobile and unable to breathe, it'd be like 70 or 80 years.
Thank you.
Yeah, did that answer? Yeah.
So in a situation where a fighter in a combative sport, boxing or MMA, kickboxing, Muay Thai, if they were knocked unconscious, they were concussed, would the Kapton then be given immediately post-fight, or is this a treatment? Can you talk about that, please?
Yeah. So this is, you can take it pre or post. Obviously, when we get it out to the market, I can see everyone, start taking it. But when you get concussed, the idea, because that's a pretty big injury, you would have medics on site. And when you get there, we would see you would want to give an IV, a big dose at that moment to really kind of help. I also see, ambulances, they carry Kaptons, and if they come across a car accident or, some of the concussion, you would probably want to give a big bolus injection of it. Yeah. Yeah. Mm-hmm.
Can you talk about the daily dose? Hold on. Somebody go to the mic.
I was just wondering when it's going to be available to the public and if it's only going to be available to just the combative sports athletes.
Very good question. We actually have our development path, because we know a lot about these molecules already. We look to be an IND enabling, and this is a part the FDA requires, and it's a year before you get into the clinic. So
Okay.
we're about a year and a half away from IND enabling, so that's about 2.5 years till we can get it into people.
So is this something that we should recommend to our combative sports athletes once they decide they're going to be like in that type of sport?
Exactly. Like if you're a parent and you know your child is wanting to get into football and all, you would recommend to start taking the Kapton. And one thing I want to say is they are very small, very stable, very easy to make, and cheap to make. We see
So
it
it'll be
one
inexpensive?
day. Yeah, it wouldn't be. We're not the type to have a big overhead. We plan it to be like a bottle of Tylenol. Now we first have to go through the clinical studies and get it out that way, but we don't want it to be something you have to get a prescription for. We want
Okay.
it to just be something anyone can go and start taking. And you would want to start taking it before you know you might be in a, in a situation like
Okay,
boxing or
Thank you.
NFL.
I have a quick question, and then the intern will bring the microphone to the other folks. The other day we heard Dr. Alif, and I may not have said his name correctly, talk about CBDs and therapeutic cannabinoids. In what way does your supplement, it sounds like it's going to be more of a supplement than a medication, compare to those methods that seem to, he indicated, did the same thing by reducing inflammation and things like that. Do these Kaptons use those same receptors in the endocannabinoid system?
It's a good question, too, because in our patent, we actually have claimed the cannabinoid receptors. Cannabinoids act like GABA, so they silence down the brain. So there are some cannabinoids we're looking at that could be Kaptonized. So again, wherever there's injury, it will go on and can react to the cannabinoid receptors. So yes, it is true. We are actually looking into that as well. Mm-hmm.
When you're talking about the daily pill, like it's an option, there's no buildup, or would they be more beneficial instead of getting that huge injection, or would that still be necessary? And what would be the benefit of taking a daily pill if you're still going to need a huge dose injection if you do have an injury?
So the huge injection we see would happen right at the site, right at the time. If someone's concussed, you'd really want to bring on a lot. But these molecules have been in people for a very long time. It's like taking glutathione. You take it over the counter. So the daily, your body can clear it. We've looked at the clearance of these molecules. We still have those studies to do, but it looks like you could take 1 or 2 a day. They'll last about maybe 12 hours inside the brain. And you'd always want it on board because you never know when something's going to happen. And with mild TBI, there's that spreading. I don't think it's fully understood why the spreading occurs at what time and speeds, because some are faster than others. But as that starts to spread, it'll just keep turning on and isolate that spreading. So we wouldn't see you have to get the big injection, only right there on site, right after some big head injury to be beneficial. Sure would. One thing about it is we call it self-dose metering, which means we'll figure out, what is the concentration to have on board. And if it's a little injury, just a little will turn on. Because I say turn on, it turns on with the amount of toxins that have ripped. So if you have a bigger injury, more will turn on. So it actually meters its own self. Does that answer? Yeah.
Let's just take two more questions because I know we have to move on.
Well, congratulations on your findings. Just a quick question for me to understand. Two parts. First part is the Kaptons could be used as a delivery system for other aids internally as a mechanism on board inside the brain. And then just curious to our fight doctors, on the excitement level, where are you at with this sort of progress for our industry?
Oh, I guess first question. I'm sorry, what was the very first question?
Sorry, just perhaps I don't understand, but are the Kapton's potential opportunity as a delivery mechanism for other aids internally on board inside the cranium?
So we've had to explain this a lot because they're like, is it a delivery? It's not a delivery system. You can't add something to it and carry something in. The more you add, the harder it is to get into the brain. It itself is the neuroprotectant, but just without that extra part. And that extra part that I'm talking about that binds to the toxins is the key to a lot of these drugs of why they're active. So it's not a delivery system. It's not a prodrug. It's not that it gets in and something cleaves. It actually is the therapeutic that turns on its activity when it encounters damage. Did that answer? Yeah.
Hi, Sarah. Tracy from Bellator.
Hi.
Can you obviously you're in a room full of people who are very excited by this prospect and very interested in seeing this move forward. Can you talk a little bit, I know you talked about where you are in the process of moving toward FDA approval and captainizing certain drugs and substances. Can you talk a little bit about where Mercaptor is in terms of what it needs to move forward in exploring this and continuing to move the ball forward so that some of the prospects that you're talking about in the eventual future can become a reality?
Yes. So we're actually pretty close because what we're turning into already has 20 years of research into it. And our biggest challenge, which we did right when we started Mercaptor, was we did an animal study with and without damage. We actually stimulated a seizure, which triggers these same sort of toxins. And it's thiochemistry. It's so unconventional. No one's ever thought that a thio would react in the brain and do this. So that was the big hypothesis. That was like, if this doesn't work, then, we have nothing. And we saw that. When we looked where we had injury, we were able to do, analysis, and we found this molecule that has been known to be GABA-like. That's that one guy we found. So because there's a lot of known there, and we've proven that you do get conversion, we got to do some tox studies to find a therapeutic dose. How much do you give to have that therapeutic effect? And we also are going to look into a few models. So we're going to do a Parkinson's, a TBI molecule, just to kind of find out, again, different injuries and different symptoms along might need more Kapton or less Kapton. And then it's actually a long plan. A lot of people at this point would start going to the clinic. We don't want to do that. We think you jump too fast to the clinic and then you're developing in clinic. So we're going to spend the next year and a half really trying to understand these molecules and which Kapton would be best. Again, we have like 6. Then that FDA approval process is 10 to 12 months. And after this year and a half, we will know enough that we know that 10 or 12 months will be successful. The only difference there is we now have to use human-grade material. So we're pretty much going to mirror that. And then within 30 days of there, you can be into phase 1. So 3 years. Mm-hmm. Did that answer? Yeah.
What hospitals are you working with, and have you published yet in medical journals?
So we have not published yet because our patent just turned to PCT, it's a few months ago. So it's completely novel. If we were to publish it right now, then you don't want to publish something without the patent. Our patent will be public in October. Again, it's,
The second question was what options?
oh yeah. So we have had conversations with the VA hospital in Menlo Park. We've been talking to scientists at UC Davis. And we're also, our TBI study is going to be at Dr. Julian Bales' lab. I'm sure you guys might know Dr. Bales. He was played by Alec Baldwin in Concussion. So he is extremely excited about it, and he's going to do our TBI research. So hospitals, not really. We're still a bit earlier to start preventing them, but we are, engaging and making relationships with, other scientists that are big in that field.
Just as a final comment, if any of the doctors want to, especially the neuro guys, or just.
Yeah, I mean, briefly, I mean, as depicted here, as advertised, it's promising. I mean, that's how medicine works. I mean, we talked about it, and just kind of breezed over the brain chemistry. But when I talked about the diffuse axonal injury and so forth, there's a series of chemical injuries that begin to take place that causes the nerve eventually to degenerate. In terms of chronic brain injuries, likewise, there's a series of kinases and phosphatase reactions that take place. This is how medicines work. They find a receptor site, they block it. So, as advertised, if this pans out, and we have some time, there has to be clinical trials, side effects, all that business, this would be the first in a line of drugs that has been shown to be preventive. Right now, there's nothing out there that is either therapeutic or preventative for chronic brain injury. And I'm including CBD oils in that too. There's no good hard studies to show that CBD oils are preventative. So time will tell. Best of luck to you. No one would be more excited than us if such a thing does come to be.
Thank you. All right, everybody. Thank you.
All right, guys, we're going to skip lunch today. No, I'm only kidding. We're not skipping lunch. We're going to be back at 1. Well, hold on. I'm getting yelled at. 1 second. 1:30?
Yeah, but before you let them go.
Before I let you go.
We're going to be selling shirts.
Oh, we're selling last call.